In the previous video, we actually go through bending and shear stresses for your solid beam. Alright, for your solid beam. And in this video, we'll talk about extending the solid beam as a sandwich beam. Alright, where you have two faces, this face and this face, together with its core. Okay, so the stresses equations will be something different from what we have seen over here. This bending stresses is my over I. Alright, for our sandwich panel equation now, alright, the stresses of the face, alright, is this one. The stresses of the core is this one really. It's different from the my over I. It's something else. Alright, so therefore, in this thing, it'll be quite tedious. So therefore, we'll slowly go through it. Therefore, just a recap is that, or just a mind map thing is that we have cleared all the way till here, right? And in the previous video, we didn't go through this one. We say that we are setting up a basis for us to start this thing. And therefore, in this video, I'll just talk about this thing first, to find the stress, or to be more exact, find the bending stress. Okay, and therefore let's start. So your beam is actually this thing, and your sandwich beam has two faces, alright, faces, and a core in between, the white color one, alright, and is being supported at these two places, alright, and this is the length and this is the force, alright. So therefore, if you were to extend this thing, alright, you have to zoom in. If you zoom in this portion, you'll come into this portion over here, alright. In fact, this is not okay. Sorry, my fault. Alright, if I were to draw this thing, so I take back my words. So if I draw this thing, this cross sectional is this one, and is also this one. This is the cross sectional. Alright, so I should have said it properly. Alright, so therefore this is the cross sectional. Alright, this is your breadth. So if you draw all the way out, this is your beam all along. Okay, hopefully this is pretty clear. So there's some symbols out there. I'll not go through it yet, but I'll just explain to you how the bending stress is being illustrated, alright, over here. Alright, so this is the bending stress for your face, alright, which is talking about either of these two sides, this side and this side. Okay, so how do you go about finding the stresses instead of my over I? Okay, and therefore m is a moment, so I will still believe that it's still the force times the perpendicular distance, where your force is divided by 2, your perpendicular distance is divided by 2, alright, dependent on your L, alright, your length. So it's still the same thing, FL over 4, because F over 2 times length over 2, which is give you this. So your moment I believe is still this one. If I have something else going on later on, I'll just update you over in this comment. Then the y in this case is not the distance from your so-called reference axis to the neutral axis. It's not this y anymore, alright, and therefore what is the y? And the y is in between, alright, h over 2. So if I were to, this is h, right, this is h, this is this length over here, alright, the full length, alright. So h over 2 is talking about this portion over here. And what is c over 2? C over 2 is actually this one, right? So maybe I should use a different color. So c over 2 is this one. So your y is in between your h over 2 and c over 2, right? Is this region over here, right? This region, and which is your face. Alright, this is for your first your top part. If you want to calculate your top part, you'll use this equation. You'll use this intervals. Alright, so over here likewise, your y, which is at the bottom one, alright, is c over 2, which at the bottom is c over 2, which is over here. Maybe I should use a different color, use a blue color then. This is your c over 2, alright, and you will have your minus h over 2, alright. Minus h over 2 is actually this one. Okay, in fact I would believe that this is minus also. I may be wrong, but anyway, so this is actually your minus h over 2. So your y is in between is in between the c/2 and the minus h/2, which is this one. Okay, and this is how you find your y. Okay, and either way your y, alright, you can choose your y to be c/2, or you can choose your y to be h/2. Alright, I'll not go into details here because I haven't do any examples, so I cannot confirm with you what values do you choose for your y. But at least you get to see the how the interval works in order to help you find the portion that you want to look at. These are the phases. This is why they are dealing with only these two parts. Alright, using this type of intervals. Okay, hopefully this is pretty clear. Then next is the D. Alright, the D is your flexural so-called rigidity. Alright, your flexural rigidity is a summation of your Young modulus, or multiplied by your second moment of area, or it's more heavy now. Okay, and most probably is because it's a beam section, so it's EI. But anyway, so it's a summation of Young modulus times I. Alright, so the fiber, not the fiber, the phase, Young modulus of the phase multiplied by bt cubed over 6. Alright, so this thing over here is the I. Alright, this thing over here is also the I. This thing over here is IC. This is IF. Alright, this is the phase, the second moment of the area of the phase. I think it's the top phase. Alright, this is the bottom phase, and this is the core, the second moment of the core. Okay, so hopefully this is pretty clear. So E is this one, it can be this one and this one, so you're summing up all together. Okay, and the I is this one, and this one, so you're summing up all the EIs together. Okay, hopefully this is pretty clear. And the T is the thickness, so you can just apply, you just know that your T is this one, you just apply your formulas lor. So your T, D, everything is already given. You don't need to do anything, you just sub in the equations. It doesn't even know how to use it. Alright, so this is the final equations you're going to use. So if happen that I would to derive this equation, alright, I think next time, alright, maybe I should post another videos. So if I were to post it, I'll just create a link over here. Alright, over here, then you can just click and see how the derivation works. Before going on, alright, the flexural rigidity is, just to recap, is the what do I say, the rigidity to prevent flexing, alright, to prevent any bending. Alright, so your beam is like this. If you have certain flexing, is kind of like bend also, or it can bend in either way. Alright, so this flexural rigidity is that if it is very rigid against flexing, against the bending. So the higher your D, alright, the rigid you are against bending. This is what it's trying to say. This is why also it includes the second moment of area. If you remember just now in the previous video, higher second moment of area means that is stiffer against bending. Same thing over here lah, but it includes the Young modulus in this case. So yeah lor. So once you found your so-called your stress of the phase over here, this is your Young modulus of your phase. So you're gonna include your Young modulus of your phase also lah. Okay. Likewise for your bending stress in the core, you're gonna use the Young modulus of your core, which will be provided to you. Alright, so this is how you're gonna find your bending stresses. Alright, so the key equations you're gonna take note are these two. Alright, and the intervals are these two, and the HCB whatever is this thing. And remember, this is the cross section. Alright, and this is the so-called the c/2, this is the h/2, and in between is your y. Alright, which is the one that you're gonna sub in over here. Alright, you're gonna know how do you do this. So I'll not go into details on how to get the value of y because I haven't tried any examples yet. But this is generally the case to solving your stuff. Coming back to this thing, we have somewhat solved for the bending stress. Alright, so in the next video we'll talk about how to find the shear stress of your sandwich structural analysis. Alright, and therefore yeah.